So thank you. The stage is yours, Iosif.
Thank you, Alexandre, for the introduction, and thanks to you and Jean for the invitation to speak here. It's a great pleasure. So my talk will be based on joint works with Mikhail Karpukhin, Nikolai Nadirashvili, and Alexei Penskoi. So in fact, these are, moment. Okay. So these are the two references that I'm going to talk about. So one has been around for a couple of years, and it's supposed to appear in Journal of Differential Geometry, and another one is quite recent. And my talk will be mostly an overview talk. So essentially what I would like to present will be some recent advances on isoperimetric inequalities for Laplace eigenvalues on surfaces, with an emphasis on maximization of eigenvalues in the conformal class. So somehow my talk will be complementary to that of Henrik Matthiessen that you've heard at the seminar a couple of weeks ago, who spoke about global maximizers, and the emphasis there was precisely what happens when you change the conformal class. So I will focus on what happens when the conformal class is fixed. So let me introduce some notation. So we're going to deal with the standard eigenvalue problem, Laplace f equals lambda f, and a complete Riemannian manifold without boundary. So my Laplacian is a geometer's Laplacian with a minus sign. And we all know that the spectrum is discrete, and the eigenvalues form a sequence that starts from 0 and go to plus infinity. And we will be interested in the following quantity. So we'll set lambda k bar be the normalized kth eigenvalue. So we normalize the kth eigenvalue in such a way that it becomes a scaling invariant quantity. So we multiply it by the volume to the power 2 over d, where d is the dimension of your manifold. And for 99% of the time, my manifold will be a surface, so d will be equal to 2. And the reason for that is, you will see it in a second. So essentially what our philosophy is that we look at this normalized lambda k, which we call lambda k bar, as a functional on the space of Riemannian metrics. So to each metric, we can associate lambda k bar. And a natural geometric optimization problem is to find the supremum of lambda k bar over all metrics. And why I'm saying that it's natural to find a supremum, because it's actually quite easy to show that infimum would be always 0. So that's not an interesting question. And moreover, in dimension 3 or higher, it has been shown by Bruno Colbois and Joseph Dodzik in 1994 that on any surface, this supremum is infinite. So in order to make the question interesting in higher dimensions, you in fact are forced to introduce some other restrictions. And for example, what you could do, you could restrict your metrics to a fixed conformal class, and then the question will become interesting again. However, in this talk, I will focus on the case when M is a surface, so D is equal to 2. And we will be interested in metrics which realize the supremum if such metrics exist. And we will call this a maximal metric. So let me first review what is known about this problem in general. So The first general result is due to Yang and Yao from 1980, which says that for an orientable surface M of genus gamma, we have that lambda 1 bar is bounded by 8 pi times this finite quantity involving the genus of gamma. And in the original paper of Yang and Yao, this quantity was equal to gamma plus 1, and it was a little bit later realized by Iosif and Elias that in fact you can make it a little bit smaller. However, in general, you don't expect that this bound is sharp. And moreover, it has been very recently shown by Misha Karpukhin that this inequality is strict for gamma not equal to 0, not equal to 2. As you will see later on, for gamma equal to 0 and gamma equal to 2, in fact, this inequality is sharp. And also, Misha, a few years ago, have extended the method of Yang and Yao to non-orientable surfaces. So he has proved the following bound that for a non-orientable surface M of genus gamma, so where gamma will be the genus of the orientable double cover, you have the following upper bound for the first eigenvalue. So what happens for higher K? Korevaar in 1993 has proved the following estimate. So he proved that there exists a constant C, positive constant, such that on any orientable surface of genus gamma, lambda K bar is bounded above by this constant times K times gamma plus 1. And this bound was conjectured by Yao in 1982. And in fact, there is an interesting discussion of this bound by Gromov in his paper on metric invariance of Kähler manifolds from 93. And it was further generalized by Gregorian, Nitrusov, and Yao in a series of papers from 99 and 2004. So this is a really fundamental result that has been used in many situations. And in 2011, Asma Hassanejad has found a very nice improvement of this bound. So she decoupled the constant, decoupled the index of the eigenvalue and the genus of the surface. So her bound is C times K plus gamma instead of K times gamma. And also let me mention that even though this bound has been stated for a orientable surface, in fact, it doesn't use orientability, and it is true for any surface. So the question that one may ask is, can this constant C be made explicit, like in the estimate of Yang and Yao for the first eigenvalue? And we will return to this question a little bit later. So let me present now some examples of maximal metrics for lambda 1, for the first eigenvalue. And the first example is due to Hirsch from 1970. So he proved that the first eigenvalue is maximized by the standard round metric on a two-dimensional sphere, and the value, the maximal value, is equal to 8 pi. So this, I remind you, this capital lambda 1 is the maximum of this normalized eigenvalue, lambda 1 bar. Then Li and Yao proved a similar result for the real projective plane. So in this case, once again, the maximum is achieved on the standard metric on RP2, and the value is given to 12 pi. So the next example came much later, and this is due to Nadirashvili from 96, who showed that on the torus, the maximal is achieved on the flat equilateral torus. And this result has been previously conjectured by Berger, so I think it was conjectured in 73. So it took more than 20 years then to prove this conjecture. And the reason is actually that this is a very deep result. And the main issue here is to prove the existence of the maximizing metric. So to prove that the maximizing metric exists and is sufficiently regular. Now, for next example is for the Klein bottle. So for the Klein bottle, the metric that is the maximizer, which is described on the slide, has been constructed in my work with Dima Jacobson and Nikolai Nadirashvili. And then Iosif, Giacomini, and Jazar proved that this is in fact the only candidate for a maximal metric. So this I will mention later on. So it's the so-called the only extremal metric for the first eigenvalue. And then finally, Karpukhin, Chanchi, and Medvedev in 2019 put together all the details needed to show that, in fact, this is the maximizer. So the metric here is actually quite interesting. So it is a certain metric of revolution, the Klein bottle, which distinguishes it from the previous examples by the fact that this is not a metric of constant curvature. So, so that's sort of the only example of a metric of non-constant curvature, of a maximizing metric that is known so far. So the other example, the only other example that remains that is known is for the surface of genus 2. And here, once again, the metric is kind of interesting. So it is a metric with conical singularities on the so-called Boltzmann surface. So the Boltzmann surface is the most symmetric surface of genus 2 that exists. And this metric comes from a double cover over a sphere. So essentially, we take the metric from a sphere, the metric of constant curvature +1, and push it on our surface of genus 2. Obviously, on the surface of genus 2, there is no smooth metric of curvature +1. So there are conical singularities. And in fact, these conical singularities, as you will see further on, it's really an important feature of this maximizing metrics. And this was first presented in our joint work with Jacobson, Levitin, Nadirashvili, and Nigam. However, we were not able to complete the proof analytically. So there was a certain piece that hinged upon a numerical calculation that we have done. However, it was not sort of entirely satisfactory that there is no analytic proof. And a very nice proof has appeared a few years ago due to Tanya and Schroeder that used some quite different ideas from the theory of minimal surfaces that, in fact, motivated us to consider the case of spheres that I'm going to talk about in a few minutes. So one final remark regarding the last example is that, well, first of all, unlike all the other maximizing metrics, this metric is not smooth, so it does have conical singularities. And also, the maximum metric is not unique. So in fact, here you have a whole family of maximizers, which is kind of interesting. So we can think about it as a degenerate maximum. So let me now talk about maximization of eigenvalues in the conformal class. And I will start with the case of the first eigenvalue. So before I proceed, are there any questions? So let me now consider the following setting. So instead of considering metrics that are maximal among all metrics, I'm going to fix a conformal class that will be this calligraphic C. And then I'm going to look at the supremum of the normalized kth eigenvalue among metrics which are varying in this conformal class. And in this case, we have the following fundamental result, which has been proved in a series of papers by Nadirashvili and Sire on one hand, and Sire-Petrides on the other hand, which appeared in between 2010 and 2019, I would say. So, this theorem states the following. So, as I already said, so let me first formulate the result for the first eigenvalue. So for the first eigenvalue, the statement is the following. So that for any conformal class of Riemannian metrics on a closed surface, there does exist a maximizing metric, which can possibly have a finite number of conical singularities. As you have seen in the example of a surface of genus 2, these conical singularities are really, it's not a technical matter, they really have to be there. And so this metric realizes the maximum of the first eigenvalue. And let me make a few remarks. So first of all, the metrics with conical singularities that arise in this context are very particular. So you can think about them in the following way. So let's, by uniformization theorem, so in each conformal class, you can fix a background metric, which will have constant curvature. So let us fix it once and for all. So it's called G0. And then we're allowing conformal factors which are smooth and have finitely many zeros. So these are so these zeros, which in the Riemannian world are illegal, here will produce metrics with conical singularities. And the cone angle is actually a multiple of 2 pi. So if r is the order of vanishing of alpha at the 0 point, then the angle is equal to 2 pi times r plus 1. So metrics which you have here are kind of very mild conical singularities. So these are cones with angles which are multiples of 2 pi. And that's, as I already mentioned, precisely what happens for the surface of genus 2. And let me also mention that very recently, there has been a different proof of this result by Karpukhin and Stern, and I suppose there will be a talk on that in a couple of weeks from now that use completely different ideas. So the proofs of Nadirashvili-Sire-Petrides are also different, but I would say that the proof of Karpukhin and Stern is even further away in terms of ideology that is being used. And it's kind of very interesting that there is this other approach that would allow us to give a similar result. So finally, I already mentioned the talk of Henrik. So there is a recent very important theorem by Matheson and Ziffert that says that on any surface, there exists, in fact, a globally maximizing metric, which is smooth outside a finite number of conical singularities that produces a global maximizer of the first eigenvalue. And once again, so the proof there hinges upon the conformal statement. So you first have to show that everything is good in the conformal class, and then you show that when you vary the conformal class, things don't get worse. Okay, so that's the story about the first eigenvalue. Now for higher eigenvalues, the situation is kind of different. And there is a new phenomena going on. So in fact, for higher eigenvalues, you have a dichotomy. So you have either the following possibility that for any conformal, so you either have for any conformal class and for any k, you either have that the maximal value of the kth eigenvalue is equal to the value, the maximal value for the k minus first eigenvalue in this conformal class plus 8 pi. And in this 8 pi, you may recognize the 8 pi that appeared already in Hersh's theorem. Or if this is not the case, then there exists a metric, once again, possibly with a finite number of conical singularities, such that the maximizing value is strictly greater than the value appearing in the previous line, so greater than big lambda k minus 1 of m plus h pi. So it's either this or this that happens. And let me explain what's going on here. So in some sense, you can think about this statement as an existence versus bubbling dichotomy. So bubbling is a new phenomena that you haven't seen for the first eigenvalue, but it appears for the kth eigenvalue. So let me produce an interpretation. So for a given k, you either have a smooth metric, possibly with conical singularities, which maximizes lambda k, or you have the following thing. So you have a sequence of metrics that exhibits bubbling in the sense that you get a surface with a sphere attached to it. And the sphere should be thought of as a bubble. And this is the sphere that is responsible for the h pi term that appeared in the previous slide. And as you will see in the examples that I'm going to present, this bubbling phenomena is actually what you see in, at least for the sphere and for the projective plane. So it's also kind of easy to see that the number of bubbles cannot be too large, so it is at most k. And that's what we observe on the sphere, in fact. So let me now state the result that we have obtained with Misha, Nikolai, and Alexei for the sphere. So for the sphere, we have the following theorem. And the good thing about the sphere and about the projective plane that will appear next, that there is just a single conformal class. So you don't have to bother about global versus conformal maximizers. So the maximizer is automatically global. So the statement is the following, that the kth normalized eigenvalue for any metric, which is smooth possibly with a finite number of conical singularities, is bounded above by 8 pi k. And moreover, for k greater or equal than 2, this inequality is strict, so it is never attained. And it is attained only in the limit by a sequence of metrics which degenerate to a union of k Taichik identical round spheres. So you can think about spheres glued to each other, which are identical round spheres. And that is the sort of limit of the maximizing metric. And in particular, the big lambda k of S2 is equal to 8 pi k for k greater or equal than 1 for any k. So what is the history of this result? So it was conjectured by Nadirashvili in 2002. And well, for k equal to 1, this is just a Hersh's theorem. And for k equal to 2, it was proved. So the proof was outlined by Nadirashvili in 2002. And then it was proved by Petrides in 2014. For k equal to 3, the result is due to Nadirashvili and Sire from 2017. And let me also mention numerical evidence, also from 2017, due to Kaolai and Austin. So let me now state sort of a cousin of this result, which is due to Misha Karpukhin from 2019, which is a similar result for the real projective plane. So for the real projective plane, it has been shown that the big lambda k is equal to 4 pi times 2k plus 1. And once again, for k equal to 1, we recover the result of Li and Yao. And for k greater or equal than 2, what we get, so we get the following surface. So you can think of it as a projective plane with spheres, k-1 spheres attached to it, the spheres are identical, and the areas of the projective plane and the spheres, the ratio between them is 3:2. And the reason for that is that the maximizer for the projective plane is 12 pi, and for the sphere is 8 pi, and that's precisely what gives you this ratio. So you have to balance the volume in such a way that you get a maximizing metric. And so this theorem was proved for k equal to 2 by Nadirashvili and Penskoi in 2018. And we have conjectured that that is indeed the case in our joint paper. And then Misha Karpukhin found a rather ingenious way to prove this result using a lot of deep results in algebraic geometry, such as twistor correspondence and other exciting things. So one application of these two results that I would like to present is an explicit Korevaar-type inequality for higher eigenvalues that I have mentioned in the beginning of the talk. So we have the following result that for any orientable surface of genus gamma, we have that big lambda k of m is bounded by 8 pi k multiplied by the integer part of gamma plus 3/2. And for a non-orientable surface, you have a similar result, but with 8 pi k replaced by 16 pi k. And the idea is actually very similar to Yang and Yao method, or its adaptation by Misha to the non-orientable case. So basically, we consider branched covers of the surfaces over either the sphere or the projective plane in the non-orientable case. And we use the explicit bounds that have been obtained for the sphere and for the projective plane. So we do not expect these estimates to be in general sharp, obviously, but it's sort of good to know that you can do it. You can find explicit constants. So are there any questions so far?
Yes. So I was wondering, you have this extended class of metrics with conical singularities to find maximizers. Would there be a way to have a class of metrics with bubble singularities so that you again enhance the space and allow explicitly these ones? Is there, would this be useful in the constructions, or?
Well, you see, the problem is that bubbles are not really this is not really a metric, right? That's the problem. Bubble singularity means essentially that you have a disjoint, the surface is disjoint, right? So, I mean, all those metrics are obtained as limits of usual metrics. So essentially, we never leave the class of usual metrics if you allow the limits. The problem is that in principle, the limit of a sequence of usual metrics can be horrible. So in this case, we're just getting some very particular singularities.
Yeah, I guess my question is, do you show that these are the only type of limit singularities that that can happen, or could there be some other?
Well, even for the first eigenvalue, yes. So for the first eigenvalue, well, I mean, are you asking that there is nothing else that could possibly happen? That's what you're saying.
Yeah, nothing else than, say, bubbles.
I don't know. I don't think that follows from the method.
All right, thanks.
I think that is, I mean, I believe that is probably true, but yeah, I don't think that we can show that there's nothing else. Okay, so let me now present ideas of the proof. So I will start with the proof of the theorem for the spheres. And the proof goes essentially as follows. So first of all, by gluing techniques that you can find, for instance, in the paper by Bruno Colbois and Ahmad El-Soufi, it's not hard to show that the supremum, the maximizer for the kth eigenvalue in the sphere, the maximal value, is greater or equal than 8 pi k, just by gluing together those k spheres that I have described. So suppose that for some k greater than 1, we have a strict inequality. So that's basically what we need to rule out. Because if this is not the case, then we'll automatically have that it is equal to 8 pi k. So we're using the existence versus bubbling argument. So if this is true, then there exists a metric with conical singularities that realizes this lambda k bar that is greater than 8 pi k. So we need to show that this is impossible. And in order to do that, we will need to use the very interesting connection between the maximal metrics and more generally extremal metrics with the theory of minimal immersions and harmonic maps. So, I mean, a minimal immersion is, well, here is the formal definition. So it's essentially an extremal of the volume functional. So you have an immersion from M to N, and if and it's called minimal if it is extremal for the function which is presented here, and M endowed with the pullback metric is called an immersed minimal submanifold. So the extremality condition for the eigenvalue, and I'm not going to present the precise formula, so this condition has been developed by Nadirashvili in his paper on tori. Essentially, it means that when you perturb the metric a little bit, the derivative is 0. I mean, I'm cheating a little bit here because the derivative doesn't always exist, but let's, for simplicity, assume that's what it is. And the key observation here is that this extremality condition is related to minimal immersions. So first, before going into that, let me just explain why minimal immersions and Laplace eigenfunctions are sort of naturally connected. And in order to do that, let me state the following result, which is a classical theorem due to Takahashi, which says that if you have an isometric immersion from a manifold into Rn plus 1 by Laplace eigenfunctions, then, and if these Laplace eigenfunctions have a common eigenvalue, then you actually get a minimal immersion into an n-dimensional sphere. And the theorem, which is due to Nadirashvili and in some form by Iosif and Elias, says that if you have a metric on a compact surface, which is extremal for the eigenvalue lambda k, then there exists an isometric minimal immersion by the corresponding eigenfunctions to the sphere of some dimension. So the dimension is clearly related to the multiplicity of the eigenvalue. And if you remember, in all the examples that I have presented, the corresponding eigenvalue was highly multiple. So basically, this result establishes this direct connection between maximal or more generally extremal metric and isometric minimal immersions into spheres. Now, there is another way to look at all this using the notion of harmonic map. So here is once again the formal definition. So harmonic maps are extremals of the energy functional, but in fact, you don't really need to read it in detail because in our setting, minimal immersions and harmonic maps are in fact the same. So we don't need to distinguish them. And once again, here is a basic example that gives you the connection between minimal immersions and harmonic maps. Consider just a minimal submanifold in Rn, and we know that, so in fact, an immersion from M into Rn is minimal if and only if the coordinate functions are harmonic in the usual sense, so with respect to the Laplacian on M. So they're just harmonic functions in the standard sense. And in a more general setting, you have the following theorem. So if you have an isometric immersion from M to N, then it is minimal if and only if it is harmonic. So minimal and harmonic is, in this case, really the same thing. And one point that I would like to emphasize, so in fact, we're going to consider a somewhat more general class of immersions. So we're going to consider branched harmonic immersions. So we will allow the harmonic map to have zeros of the differential. So, and these are the points that in our setting will produce conical singularity. So once again, there is this whole theory that studies this kind of immersions. So basically, to summarize, so we have connected the study of maximal metrics for, and more generally extremal metrics for eigenvalues to a whole new field in differential geometry and geometric analysis. So the study of minimal submanifolds and harmonic maps. And that opens up a huge toolbox because there are lots of results that are known. So this is a well-developed subject. And basically using those tools, we're able to complete the proof for this sphere. So in this particular case, there are two key observations. So one is a result which is due to Calabi and Barbosa that says the following. So suppose you have a map from S2 to Sn. So suppose it's a harmonic immersion, possibly with branch points. Then you have the following. So you have that the area of your sphere with a metric which is the pullback of the standard metric on Sn has to be a multiple, an integer multiple of 4 pi. So in fact, there is a lot of rigidity in this picture. And moreover, so this integer d that is defined through this is called the harmonic degree of the immersion. So this is one result that we need. And another result that is much more recent, which is due to Edziri from 98 in general, and for in some special case, it is due to Manchel and Ross and Nayatani, that if you have a large harmonic degree, then large harmonic degree necessarily means that your sphere has many small eigenvalues. And then if you put this together, you can view it as follows. So suppose you have an extremal metric for the sphere. So then by this theory that we have developed, it has to correspond to some harmonic immersion to a sphere. And then you're stuck with the following issue. So we want to maximize the normalized eigenvalue. So for the normalized eigenvalue, so you need to have both the area and the eigenvalue large enough. However, here we cannot achieve that because if the area is large, then there are many, many small eigenvalues, and therefore your eigenvalue is actually small. And that leads to a contradiction with our assumption. So that shows that for k greater than 1, for any extremal metric for the kth eigenvalue, lambda k times the area is in fact less than h pi k. And that essentially completes the proof of the result for the sphere. So obviously this Edziri's theorem is a major step. And once again, we were sort of lucky to find it because it is presented in a context which is completely different from spectral geometry. So he was really interested in theory of minimal surfaces there. However, it does solve the problem for us. Okay,
Can
so
I ask a question, Iosif?
yeah.
It's Alex. So to prove the bound of 8 pi k, you need to use existence of the extremizer, right? Like
Yes.
Okay. Yes, that's my question.
Yes,
Thank you.
absolutely. So both for this theorem and for the theorem, for Mishra's theorem on the projective plane, and in fact for Matheson-Ziffert theorem about global maximizers, so you do need to know the result, the Nadirashvili-Sire-Petrides theorem. So it's sort of the basic fundamental block of everything. Other questions? Okay, so if there are no further questions, let me move on and present some ideas of the proof of the theorem of Nadirashvili-Sire and Petrides. And I'm going to follow the paper that we have recently written with Nikolai, Mikhail, and Alexei, which essentially, so the origin of this paper was to try to explain and present in more detail the approach that has been originally presented in the papers by Nadirashvili and Sire. So this approach, as I said, is somewhat different from the approach that appears in the papers of Petrides. So there are certain similarities that I'm going to comment about. However, so basically my point here is to try to explain the some general ideas of the proof. So first point is to, instead of looking at eigenvalues of metrics, try to expand the space of objects at which we're looking, and instead of metrics, look at what is called the radon measures, and look at the eigenvalues of radon measures. And here, let me mention a very important paper by Gerasim-Kokorev from 2014 that has developed this approach in the context of maximizing metrics. So basically, in practice, this means the following. So let me explain. So since we're constrained to a given conformal class, so we fix a background Riemannian metric, which is an honest Riemannian metric, say metric of constant curvature. And we look at the following eigenvalue problem. So we take a function v, which is non-negative, and say in L1. And we look at the following eigenvalue problem. So this v represents, if you wish, the conformal factor. And this v will be also responsible for the corresponding measure that will be associated with this problem. So this is no longer an eigenvalue problem for a metric, but it's rather an eigenvalue problem for a measure. And we will, like the next step that is done, so instead of looking at the maximization problem for the eigenvalues, so there exists a way that I'm not going to describe in detail to restate this problem as a maximization problem in terms of this potentials v. So you can cook up some Schrödinger operators and look at a certain maximization problem with the following important difference. So you're actually largening your space of potentials. So you're allowing your potentials to have negative values. And that gives you more freedom for perturbations. So in particular, the extremality condition that you obtain is much nicer. And a key observation here, so these potentials will be bounded. So in fact, what we will consider later on, so we will look at a sequence of those potentials as their norm is allowed to take large values. And the key thing here is that that if you start with this more general problem allowing potentials to have negative values, then the maximizing potentials will in the end be non-negative. So it's kind of a rather general idea in variational calculus. So you first allow a larger space, but then you show that the maximizers in fact have the nice properties that you would wish them to have in the very beginning. And a good reference for this step is the paper of Girouard, Nadirashvili and Sire from 2016. So the maximizing potentials in the end turn out to be non-negative as we wish. So basically, the upshot is that for a given n, so we consider potentials with the L infinity norm bounded by n, and for this n, we can produce, for this picture, we can produce a maximizer. So now we would like to relax this condition that our potentials are bounded by n, and we let n go to infinity. And the result of this step is as follows. That for each k, so k, I remind you, is the index of the eigenvalue that we're maximizing, we have the following sequence of maps. So M will be the index that parameterizes our maps. So M goes to infinity corresponds to that large N goes to infinity. So you have a sequence of maps from your surface into Euclidean space of some dimension d, which has the following features. So first of all, these maps are solutions of our eigenvalue problem, and the corresponding solutions, the corresponding lambda km, the corresponding maximizers, they converge to the maximizer of the eigenvalue in the conformal class. There exists a weak limit of those maps to some map phi k. So this is a weak limit in H1, and there exists a limit also in L2. The absolute values of those phi k are equal to 1. So that essentially means that we get a map into a sphere. Again, not so surprising given that we know that the maximizer should be a map into a sphere.
Iosif, can I ask a question?
Yeah.
Why are the maps all going to the same RD with the same D?
Well, you can choose like a large, you can bound, say by the bound of multiplicities, you can assume that there is some
okay, so there might be some dimensions that are not used.
Yeah. And then you have a weak convergence of the corresponding radon measures corresponding to those maximizers. So that is the picture that you get out of this approach that I have just presented. So unfortunately, this is not quite good enough. And it's not quite good enough for the following reason. So the key here is that, so on this slide, sort of the nice things are colored with blue color, and not so nice things are colored with red color. And I'm going to use this convention later on. So the fact that we have a weak limit in H1 turns out to be not good enough. And here is the reason. So basically what we would like to do, so we would like to take those solutions of the problem where we have imposed this assumption that the norm is less or equal than n, send n to infinity and say that, okay, so these solutions will converge nicely to the solutions of the unrestricted problem. And that doesn't quite work for the following reason. So let me show you this diagram. So on the left, we do have convergence, just because you have weak convergence. However, on the right, because here we have convergence in measure, so remember that we have also this potentials Vmk, and the fact that phi mk weakly converge to phi k that doesn't allow us to deduce that you do have convergence here. So you need a stronger convergence, something like a uniform convergence. And that's indeed what we get, and that's quite involved, in fact. However, you need to be a little bit careful. So let me now describe how we do get a strong convergence of the maximizing sequence of potentials. And the key here is the notion of good and bad points. So what are good and bad points? So bad points are points such that in arbitrary small neighborhoods of those points, the first Dirichlet eigenvalue is not large enough. Now, if you think about that, how possibly on a very, very small neighborhood of a point, a Dirichlet eigenvalue can be still not very large? Well, the answer is you need to have concentration of measures. So if you have a lot of measure concentrated near a point, then no matter how small a neighborhood you take, in fact, the neighborhood is not so small from the viewpoint of the volume. And therefore, the first eigenvalue doesn't have to be large. And one can show, so these are the points where, as you can guess, are precisely the points which would lead to bubbles. So one can show from the variational arguments that there are at most k bad points, so at least there is a finite number which is controlled. And so these are precisely the bubble points that will appear, and we know that they will appear, so that's not such a big surprise. And the proposition that we prove is that given a good point, so a point where you don't have this issue, then in fact you have strong convergence. So then there is a neighborhood such that your maximizing sequence converges strongly in H1 to phi k. And this could be viewed as a sort of what is called an epsilon regularity type statement. So in geometric analysis, these are statements which say that weak convergence implies strong convergence, provided something is small. And here, by small, we mean this 1 over, the small parameter is 1 over the first Dirichlet eigenvalue. So we do have strong convergence, however, outside neighborhoods of some finite number of points. And then from the strong convergence in H1, by standard arguments, one can show that in a neighborhood of a good point, you will have actually uniform convergence except on a set of arbitrary small capacity. So you will get more or less what you hoped for. And then if you combine those results with the ones that we obtained in the first part of the argument, so namely that your functions are solutions of this equation and that their norm is equal to 1, then you get the following, that you get that your limiting measure on the set of good points is given by this formula, and that phi k is a weak solution of this equation. And this is exactly, as one can observe, just the equation that gives you a weakly, what is called a weakly harmonic map. So basically, this means that phi k is a weakly harmonic map to a sphere. And we know from general theory, so there is a theory that has been developed by Sachs-Uhlenbeck and Elaine, that such a map, in fact, extends to a smooth harmonic map to a sphere. And so recall that we had just finitely many bad points, so we just had to sort of remove those singularities, which is possible to do. And we got the following result. So we show that there exist at most points, which we denote by P1, PL, and a harmonic map phi k from our surface into a sphere such that the limiting measure looks like this. So it has a smooth part, which is given by the first term, and a singular part, which is essentially a weighted sum of Dirac delta functions at those bed points pi, which are the essentially the bubble points. And also note that the differential of phi k can vanish, and those points where the first term vanishes will correspond precisely to the conical singularities of the limiting measure. So this leads us to the last step of the argument. So now we need to deal with those bubble points. So we need to show that, well, either there are no bubble points as for the first eigenvalue, or that in fact, when you look at the sequence of metrics that converge to the maximizing metrics, then your eigenvalues converge to what they should converge sort of in the good situation. So for the first eigenvalue, dealing with bubbles is not that bad in the following sense that there are no bubbles, right? And the key result here, which is a very important result, which is due to Petrides from 2014, he proved that for any conformal class on any surface, the maximizer of the first eigenvalue is strictly greater than 8 pi. And in fact, originally the theorem of Nadirashvili and Sire had this assumption. So they proved it under the assumption that lambda 1 is greater than 8 pi. So this assumption has been removed by Petrides. He showed that, except that on a sphere, that never happens. So we do have this. And then we have a result that appeared in some form first in Nadirashvili's paper in 96, and then was proved by Girouard and in a slightly different setting by Korevaar, that if you have a sequence of measures which converge to a Dirac measure, then the supremum of the lim sub of lambda 1 is less or equal than 8 pi. So basically it means that if the big lambda 1 is greater than 8 pi, then a Dirac measure is not a good maximizer. And finally, there is a lemma that you can find in a paper by Korevaar that says that if your measure is discontinuous, it means that you have a Dirac measure and possibly some other parts of the measure, then in fact the first eigenvalue is 0. So once again, that means that you cannot be that cannot be a maximizer. So putting this together implies that the limiting measure has no bubbles unless we're on a sphere, because on a sphere we do have 8 pi as a maximizer, and on a sphere we know the answer by Heshe's theorem. So the case of the sphere has already been covered. So that is the argument for the first eigenvalue. For higher eigenvalues, the situation is much more complicated, and I'll just present a very, very superficial description of what's going on. So in fact, the construction of the dealing with the bubbles in higher eigenvalues occupies probably almost a half of our paper, and it's a large chunk of the proof in the paper by Petrides. And in fact, difficulties that we encounter are kind of similar, even though we use different approaches. So the Petrides has been using heat kernel techniques. I mean, we're using maybe kind of more direct approach, but essentially, I believe that on the level of ideology, it's all very similar. And in fact, it's also very similar to what is called the bubble tree construction for harmonic maps. And here a reference that could be useful is a paper by Parker from 96. So essentially what can happen, so you might have, as I said, so you can have bubbles, but what is a bubble tree? So you can have bubbles on bubbles. So you get one sphere and then from that bubble sphere, you get another bubble, and then from that other bubble, you have another bubble, and so on. And you have lots of issues there. So in particular, you need to show that this bubble tree is finite, so that that procedure at some point terminates. And the approach that we're taking is that we show that, in fact, if you rescale appropriately, then each bubble can be viewed as a sphere. And on this sphere, we can repeat the construction that we have presented before. So you can once again choose a maximizing sequence of potentials and so on. And then if you have the secondary bubble, then we apply the process inductively. And you have to show that at some point this process will terminate, which is indeed the case because you can show that small bubbles can be ignored. So sort of on a naive level, if you have a very small bubble, so a very small sphere, then the spectrum, like the eigenvalues that will be produced by the sphere will be very large. So they will be larger than the maximizer you're looking at, and therefore they're sort of irrelevant. So it's better from the maximizing perspective to disregard those so that there are no small bubbles, and that allows you to control this process.
Can I ask a question, Iosif?
Yeah.
If you have a bubble appearing, don't you have a new zero appearing in the spectrum because it's splitting from the?
Well, you do, but that's okay. So that's the reason. So that's the reason that having sort of an extra bubble that doesn't really lead to anything is bad.
But couldn't you just say you cannot have more than k bubbles because you would have more than k zeros?
Well, the problem is that in this argument, and that's sort of the main difficulty. You need to show that when you have a limiting sequence, that that the eigenvalues converge to what you expect it does converge. So it's not a priori clear that you have convergence of eigenvalues. It's true that if you take the limiting object, there you have a lot of zeros in the spectrum. But why do you have convergence of the spectrum?
I see. Okay.
That's the problem.
Thank you.
Okay. Okay, so I'm almost done. So let me conclude with some open questions. So first question is, so in the examples that we've seen, so for the sphere and for the projective space, for projective plane, we did have observe the bubbling phenomena sort of at its maximal capacity. So we had as many bubbles as we could possibly have. So do smooth metrics with conical singularities ever arise as global maximizers for high eigenvalues on surfaces? So we don't know that. And actually, I don't know the answer to that question. Another question is, and that's a whole large field to explore. So what happens in dimension greater or equal than 3? So in particular, well, we know that the conformal spectrum is bounded in any dimension. So which singularities may conformally maximal metrics, say for the first eigenvalue, have in dimension greater or equal than 3? So can one find some analog of this existence versus bubbling result for higher eigenvalues, or like, is there any structure of, if you wish, of singularities that maximal metrics have in dimensions higher when you fix a conformal class? And again, as far as I'm concerned, there's very little known about that. I'm not aware of any real numerics. So it's a completely open field of research. So thank you very much.
All right. Thanks a lot, Iosif, for the very nice talk. It was very interesting. Does anyone have any questions about the talk that we just heard?
Yeah, so there was a question in the chat, but it's has been already answered by Nikolai. So indeed, the bubble points, they do not correspond to conical singularities. So bubble points are precisely the points where the mass concentrates, and the conical singularity is the singularity where the mass vanishes, if you wish, because they correspond to the zeros of the conformal fact.
So we have another question now from Selma Yildirim, who's asking if there is a relationship between lambda k of S2 and lambda 1 of a surface of genus K.
Lambda k of S2 and lambda 1 of a surface of genus K. Well, not that I know of, so why there would be a relationship?
Oh, so for S2, the first eigenvalue was 8 pi, and for surface genus K, it was 16 pi, right? For that was already in your slide, I guess.
So maybe I misunderstood your question. So
so like a slide before, please. Before, so that was very, I don't know much about. Oh yeah, right there. So just one more. Yeah, so right there. So the lambda 1 of genus 2 is 16 pi. So for the sphere it was 8 pi and then 16 pi.
Yes, yeah, sorry, yeah. So of course there is a connection. So the connection is as follows. So basically, so this this maximizing surface of genus 2 is constructed as a branched double cover over a round sphere. So this 16 pi precisely comes from the 8 pi downstairs, but since it's a double cover, so you have to double the area.
Okay, so and then in your result for lambda case for the sphere, it was 8 pi k.